Hello, this is the AFNI Academy. Today we'll be discussing regions of interest, also known as ROIs. This part will be the introduction to the ROIs. Okay, so let's get started, and let's start with a definition of what is an ROI. So, an ROI is the region of interest, and we use it as a mask of voxels. So in AFNI, ROIs are stored like any other data set, and they can be stored as head brick files or as a nifty data set. And usually we'll use positive integer values for every voxel that's considered part of our ROI and zeros for outside. So we can see that here in this diagram where every blue square is a voxel. The ones that are filled in with red have a value of 1. And the ones that are black have a value of 0. So we'll count all the ones that have a value of 1 as our ROI. And you can see they don't even have to be connected. They just have to be somewhere that's a non-zero voxel. And usually we will store these as byte integers. And that's because it saves disk space and it saves memory. But we can also use short integers. So either one is okay. Other programs may use polygons or vertices to save ROIs. That's not how we do it in AFNI. We save these as just a bit mask. Okay, so now that we know what it is, how do we create it? Well, we've got a few different ways to create ROIs. One, we can draw them. And we have another video showing how to draw data sets. You can take a look at that. So you have to know how to draw these neuroanatomical regions, so that means you have to know something about neuroanatomy. And so it requires knowing something about the structure of the brain. A second method is to generate clusters. So let's say we've analyzed a functional data set, and then we take clusters of activity and they look like these. We have to set some sort of threshold. We have to define what a cluster is, how voxels have to be neighbors with each other, and then we can generate a cluster. And we'll show a little bit about that. And finally, you can take it from some other source of information, like an atlas. So someone else has drawn these regions and created an atlas for you. In AFNI, we have a lot of different atlases. We'll show how to access those and how to use those regions that are in the atlases. You can also get regions from FreeSurfer or from 3D Seg to segmentation, other kinds of classification algorithms. And you can also just put spheres around different coordinates, and we'll talk about that. Okay, so the first method is to draw your own ROIs. As I said, we have another video for that, so check in the description for how to access that video. But if you are drawing a lot of ROIs, consider special drawing tools like a stylus with a touch screen or Wacom Cintiq, or other software packages like MIPAV or Amira. If they support nifty output, then we can take those as input. So another way is to generate clusters. Now we have another video on how to use our Clusterize plugin in the AFNI interface, and that's a great way to see where clusters are. And that looks generally like this. You go into the overlay panel and click Clusterize, and then you define what a cluster is, and then you can look at a report for all the clusters. But and these are some of the other features from the report. You can jump to each particular cluster, flash and show those clusters. You can save the mask from within the interface, and you can also generate a 3D clusterize command. So we'll talk about that. So here's the 3D clusterize command. 3D clusterize is a program that does the same thing as the GUI version of it. You tell it how many voxels have to be in a cluster, what kind of cluster. Is it is it a one-sided test that you're doing for this, or you're looking at both positive and negative values? And so here we're usually looking at both positive and negatives. So we want something that's more negative than -2 and more positive than +2. And we'll take an index of to threshold on from subbrick number 2, so the third subbrick in our data set. And we'll apply it to the first subbrick, the second subbrick in our data set, subbrick number 1. And then we will define our clusters as being defined by nearest neighbor setting of 1, which means all the faces of the clusters have to touch each other. So you can have them clusters defined by faces, by edges, or by corners. So this is the most direct version of clustering, is that only the facing voxels are counted together in clustering. And what data set is used as your input? So here we're using a functional output data set. And then what do we want to call our output? So these are where the clusters are going to go. And this is what an example slice is from that output data set. Okay, and it also generates a report for you. So we have this cluster report. You can see that these are sorted here by the volume. So the largest volume cluster is shown first, and then it shows you various things like the center of mass and the ROI coordinates from right to left, anterior to posterior, and inferior to superior. So these are the coordinates here. Then it shows you the locations, the extents of each of the cluster, minimum and maximum in each of the directions, and then the mean through the cluster, the mean of that data subbrick, subbrick number 1, and then it gives you the standard error, and then it also gives you a peak value. So what is the peak value, and then where is that peak value's location? So all useful things to get out of clusters. So a third way to get ROIs is from atlases. So we can use the main atlas accessing program in AFNI. It's called whereami. So this can extract the ROIs from the atlases, and we can do it with a symbolic notation like this. So we say whereami dash mask atlas region, and then the name of the atlas, and then whether we want left or right, or we can just put nothing in between, just put 2 colons next to each other and keep this blank, and then the name of the region. And so here we're using the Talarank daemon. And you can use any atlas that you want. Here we can find out which atlases we have with the whereami-show atlases. That gives you a list of all the atlases that are available to AFNI. If you want to see all the regions that are available, you can do whereami-show atlas code. If you give it, if you tell it whereami-atlas and then TT daemon or one of the other atlases, like the M&I Glasser HCP v1.0, you can combine it with that show atlas code, and it will show you only the atlas codes for that atlas. So here's another example where here we give it not only the name of the atlas and we say both sides, but the name of the region is for a left region, so that's just included in the region's name. And then we'll give it a prefix, which we didn't do before. By default, you'll get the name of the atlas with a period, and then the name of the region, and then a period, and then the side. But you can also give it what you want to call the output as the prefix here. But you don't have to use whereami. You can use any AFNI command to generate the same kind of output. So let's take the same region that we looked at on the previous slide, and we'll use 3D Calc instead. So I'm using 3D Calc here as an example of an AFNI command, but it can be virtually any AFNI program. It will be able to read atlases by name or by index. So let's start with the index. Here we will specify the name of the nifty data set. Here, we're not naming the atlas here, we're naming the nifty data set. And this could be an ROI data set that you've generated yourself. You've drawn the data set or you've clustered it, and then you tell it what index you want to go after. For atlases, those have labels in the header, so we don't have to do it by index. We can do it by the name instead. So let's go through the first command, 3D Calc. This is an AFNI program that does calculations with images. Okay, and we're doing the simplest possible calculation. We're saying take this image, and we'll use this range selector, this less than and greater than symbols, and put in an index in between that says this is the index that we want to get at. And then the expression is just use the value of this A data set that's been limited to this 169 value, and then save it as with this output name. So this output will be called left front OPERC plus TLRC. This atlas is in MNI space, but we still use the view part of the name to say that it's in a standard space. But rather than use 169 or any index value, we recommend that you use the name of the label instead, the atlas region name. This is preferable, and the reason that it's preferable is that if the atlas is updated for some reason and they've added some more regions or subtracted regions from that 169 may not be reliable. So here, if you specify it by this way, you'll always get the region that you expect and not another region. Okay, so this example is almost the same, except for that part. Okay, another example with how you might use atlas regions with AFNI commands. Here's another 3D Calc command, and here we'll look at calling this atlas, so the macro label atlas from Eichhoff and Zillis, and we will look at the hippocampus. And here's an example of the output. So we'll take the hippocampus, we'll take some f-stat that we've calculated ourselves and resampled out to 1 millimeter, and we'll say anywhere that wherever the hippocampus is, we'll take a step of A, so that says wherever the hippocampus is positive, we will multiply it times the f-stat. So this will end up leaving just the f-stat within the hippocampus of this macro label atlas. So this becomes step of A is 1 for the hippocampal area, and then multiply it times the f-stat. So 1 times B is B, so we'll get that f-stat back. And then this is the output. So a simple command of how to use AFNI with ROIs like these atlas regions. Here's another example. Here we will have, we'll look at two different atlases. And so here we'll have the Telerik daemon, and we'll compare it to the macro label atlas and look at the amygdala from each. Okay, so the amygdala is specified for both atlases, and we'll say wherever the amygdala exists in the Telerik daemon, we'll take step of A, that's give it just a value of 1. The amygdala doesn't have an index of 1, but step of A will turn that into a 1 wherever it's positive. And then wherever the Eichhoff-Zillis macro label atlas is positive, we will have 2 times that step. Okay, so now we'll add 1 plus 2. So if it exists in the Telerik daemon, it will be 1. If it exists in the Eichhoff-Zillis macro label, the pseudo-architectonic atlas, it will be 2. If they exist in both, it'll be 1 plus 2. So that is 3. And so we will get 3 possible values. And we'll call the output compare.maps. It will be compare.maps plus Talarak. We'll try to make AFNI show it with an integer color map like this one by setting this in the header to use an integral color map. Okay, so here you can see that the Talarak daemon shown in salmon comes a little bit under here, and this is it has a value of 1. And where it's purple, that's where the cytoarchitectonic data set, the macro label atlas, shows is there, and that's a value of 2, and where it's green has a value of 3. So this shows us how to use both atlases. This is a way to compare these two atlases and to realize that atlases aren't exactly right, and they disagree because of how people drew the regions in the first place and how they generated them. So you can't completely trust an atlas, and these regions are subject to some negotiation, let's say. Another way to get regions, ROIs, is to generate them with spheres. So let's say, for instance, you've done an analysis before. You can get locations from that analysis, or maybe you're getting coordinates out of the literature. So with some set of coordinates, you may want to put spheres down into this data set, and so this is how you might do that. Okay, so we're going to move some of the data that's in our AFNI Data 6 AFNI directory into Talarak space with this add warp command. This is one way to do that, and then we will clusterize, save the clusterize table out of the clusterize interface, and then that clusterized table can be extracted by itself into an XYZ table in RAI coordinates. That RAI goes from right to left, anterior to posterior, and inferior to superior. This is just one example, and we will create a new data set that's in RAI coordinates with 3D resample. And finally, we'll use this 3D undump command. So 3D undump is the program that generates these spheres in a data set. And then if here we're saying put a 7.5 millimeter sphere, that's the radius of the sphere, in using this data set as our master, that defines our grid, and use the set of XYZ locations that we generated just above here. And this is what it looks like in AFNI. So generating ROIs with spheres is actually pretty handy. We have to do this pretty often. If we know something about what coordinates we're interested in, we can put those spheres down and use those as our ROIs. Okay, so once you've generated an ROI, usually if you've drawn them, you usually draw them on the anatomy that has high resolution, but we're almost always dealing with EPI bold data, and that has low resolution. So we have to go from this high resolution matrix to a low resolution voxel matrix. So how can we do that? What do we do here? So here we've got these blue squares are our original matrix, and we go to our low resolution. Now if it's completely filled, that's pretty clear what to do. If it's completely empty, going to low resolution, that's pretty clear. We don't have to fill it. But what about in these partial situations where it's halfway, or if it's only a third filled? Then what do we do? So if we have data sets that are very narrow, we can have only a very small bit covered by this low resolution. Do we still want to count these ROIs? And so we have a couple programs that deal with this how to go from high resolution to low resolution. So let's look at one. So one of these programs is called 3D Fractionize. This is concerned with the fraction of the voxel that's covered going between these resolutions. So we have our ROI, that's our input. At high resolution, we want to put it onto a low resolution template, maybe our API resolution, and we wanted to clip it at some fraction. What fraction do we pick? So you might want to pick at 50%, 0.5. And for an ROI, you want to preserve the value that it is in the original data set. If it has a value of 4, you don't want to say if it's only half filled, it's 2. We want to keep that value of 4. And then we just the name and the output, the usual specifier in AFNI commands of what to call the output, the prefix. So some examples: if you have a voxel that's only 80% filled, you would keep it. If it's 30% filled, with this cutoff, you're going to drop it. It will be 0 in your output. And again, we want to preserve the values. So 80% of 4, we don't want 3.2, we want it to stay as 4. Okay. Now, 3D Fractionize is a great program, but it's very slow, and it deals only with affine transformations anyway. So usually, in almost all cases, we will just do 3D resample. And this is a much simpler program. Effectively, it does something like a 50% clipping. It's not exactly that, but it's something like it. And you give it similar kinds of input. You give it the high resolution ROI that you've drawn, and then you give it the name of the output, the low resolution data set that you want to resample to, and we have to remember here that we want to have an interpolation mode of nearest neighbor. So what does nearest neighbor mean? This is the location. It doesn't average on the output. It finds the location in the original source data set that's closest to the voxel that we're moving our grid onto. So it will find the center of a voxel that's nearby. What's the closest center voxel from the original source data set? So here's an example using 3D resample. Here we've drawn an ROI on the high resolution data set, and then we resample it to our low resolution data set. And it looks a little bit different. Some things are different because the grids are slightly different between these two data sets. In resolution and in location, they're slightly shifted from each other too. Okay, this is the command that we use. This is exactly the same as the one before. You can do this command in the AFNI Data 6 ROI demo directory from our class data, if you like. Okay, so we resampled from 0.9 by 0.9 by 1.2 to this low resolution data set. And why do we do that is because all of our data is at that low resolution. We don't actually need it at the high resolution, but we do need to assess it on our actual data that we've analyzed. Another thing that you can do is that's something like this resampling. It's moving the data around. We want to move our ROIs. So we may have ROIs that are in standard space, and we may want to move it to our native subject space. This is very commonly done in animal studies, or if you have subjects that you don't want to move them around too much in terms of the transformations. You just want to put everything in the original location if you're doing high resolution layer work, for instance. So you may do something like this. So let's say you've got these are three different ways that you would do this from standard space using basically 3D Alineate, 3D Warp, or 3D Fractionize. This is the program we just talked about. I will skip over this because usually we aren't doing these with affine transformations anymore. we're usually doing this now with nonlinear transformations. So with a nonlinear transformation, this is a little bit more complicated, and in this case, we're going to combine affine transformations with a nonlinear warp, and here's how you might do that to go from the standard space, to move an ROI from the standard space into the native space. This works for any kind of data, but here's one place you would do it. So that's with 3D and warp apply. I'm putting these here just as reference for when you would need to do this in the future. Okay, there are a couple other ways that you can do it to generate these kind of combined warps with 3D and warp CAD or 3D and warp calc. We would generally do this with 3D and warp apply.